All right, so some properties of a derivative. So we talked about a function being differentiable if the derivative exists, right? So we see that verb coming in. So it's differentiable if the derivative exists, and then if the derivative at a point exists, and then if it's differentiable on an open interval. Endpoints are really tricky, so we generally don't say a function is differentiable at an endpoint. But on an open interval, so if it's differentiable at every point in that region, right, then it would be differentiable on that open interval. Endpoints are a little tricky. Why? Because think of how the derivative is defined, right? So the derivative, so f prime at a, right, is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h, right? And so here, right, because we have a two-sided limit, that's why endpoints are a little tricky. Like, how do you talk about the other side? When you're like, well, there isn't a function, so it isn't defined. But then on the other hand, you can say, well, there isn't a function, so it has to be defined. So mathematicians get worked up in a tizzy over this because it's sort of like a logic conundrum that we haven't quite come to an agreement on. So that's why we just in this course we're not going to talk about endpoints being differentiable. Okay, just to avoid the issue. Okay, now important, very important theorem. And if you mix this up, this is going to be not good for you. Okay, so we have a theorem that says if it's differentiable, then it's continuous. So this is what I would call our hypothesis. We know this is true. We assume this to be the case. And then what follows, this continuous piece, would be a conclusion. So if we can show that it is differentiable, then we can automatically say, yep, it's going to be continuous. Okay? And so a little proof that's actually kind of beautiful goes like this. All right, so let's look at f of x minus f of a, okay? And this is, by definition, also equal to f of x minus f of a, okay? You're like, well, gee, this is how we're starting a proof. This is kind of silly. But then what we're going to do is we're going to multiply by x minus a to numerator and denominator on the right side. So it actually doesn't change anything, right? Because that's 1. Okay, so then I'm going to have, this is equal to f of x minus f of a all over x minus a times the quantity x minus a. Okay, not a big deal. And now I'm going to apply a limit on both sides. And the limit I'm going to apply is as x approaches a. Limit of f of x minus f of a. That's over there. Do it on this right side as well. Limit as x approaches a of, and then I have to do the entire thing, f of x minus f of a all over x minus a, and then times x minus a, because I don't know that these limits exist independently yet. Okay? All right. So now I'm running out of room, so I'm going to come up here. Okay. And so before I go further, let's see what we remember about the definition. So we should remember that differentiable is that definition that's at a point, right? And actually I should change that to maybe at f prime of x. Okay. For continuous, right, what that means is that if we look at the limit as x approaches a of f of x, that's equal to f of a, right? Oh, that's kind of smelling like the left-hand side, right? So the limit, I mean, we should be able to separate those because the limits exist independently, or do they? I don't know. Okay, more on that soon. Okay. But now I'm going to say that if we look at this limit as x approaches a of f of x minus f of a, right? I can say that this is now equal to, looking at these things independently, right? This first part is our average rate of change. And so that one I can say that exists because of the differentiable piece. And then the second piece, if I look at that, it's just a linear thing, so it exists. So it allows me to say by limit laws, I know those limits exist independently, and so I can break them up. I'm just going to leave little placeholders. I'll let you fill it in on your own. Okay, so it'd be limit of that first part of the product and times limit of that second part of the product. And so then if I look at this, this would be f prime of a times, and then if I evaluate that, that's 0. So then in all on the right-hand side, I just get 0, right? Okay, and then if I look at this a little bit, so I know that the overall limit exists, and I know that f prime of a exists. Okay, so then does the limit of f of x at a exist? Well, that's where we get into maybe a little trouble, but what I am able to do is break this up and do like limit of f of x. Because it's differentiable at this place, I can actually break the limits up, and I can do like limit as x approaches a of f of a, and that's equal to 0, and then move that to the other side, and I just end up with the right-hand side being f of a, because the limit is of this is a constant in here, so I can just move that over, and then I get continuity from here. Okay, so just wanted to show you that proof. It's kind of fun. Now I want to be very, very clear. The reason I mentioned that you need this sort of hypothesis and conclusion order is because the converse is not true. Okay, absolute value of x is a counterexample. So if we think about absolute value graph, right, it is continuous. We can draw it like this, but then particularly when we look at the v part of the absolute value graph, that's going to not be differentiable. And we'll see more on why soon. But so that's not true. It is, however, true that if we look at the contrapositive, and I'll write it out, that is true, okay? And so what this would say is that not continuous, and I sometimes abbreviate continuous as CTS, not continuous. Okay, if we know it's not continuous, then it's not differentiable. Okay, and you're kind of like, well, duh. You can probably think of a graph that is discontinuous, right? And then would that mean that it's not differentiable? Yeah. So something like, the floor function, right? We look at that thing, it's like, okay, we have a lot of jumps and breaks, and can that ever be differentiable because of the limit, right? Think about limits at those step points, at those discontinuities. No. Okay, so since we have discontinuities, we can't talk about a limit there, and therefore, well, sometimes I should say when we have a discontinuity, sometimes we can't talk about a limit, and so then therefore we can't conclude that it's differentiable. All right, so some important properties, again, the biggie being that if we can say that the derivative exists for a function, then we automatically get continuity.